Welcome to this explainer. Today, we're taking a university-level deep dive into the nuts and bolts of industrial automation. Specifically, we're going to master programmable logic controllers, or PLCs, and exactly how they manage on-off temperature regulation. If you're looking to really understand how these systems maintain such precise environmental control, you are absolutely in the right place. To kick things off properly, I want to formally introduce our source material. As it says right here, this educational material is prepared by Dr. Nima Mahdian. We're going to be unpacking the concepts and diagrams strictly from Dr. Mahdian's research today. This ensures we're getting a rigorous, true engineering-grade understanding of the whole process. Okay, let's just dive right into it. Here's a quick look at our agenda for today. We'll start with an introduction to temperature regulation, move on to hardware architecture and routing, look at the ladder logic implementation, break down the system state matrix, and then wrap it all up with hysteresis and system dynamics. It's essentially a full journey from physical heat right down to system dynamics. All right, Section 1, Introduction to Temperature Regulation, Physical Meets Digital. Let's get into it. Drawing straight from Dr. Mahdian's foundational presentation, we're really focusing on the holy trinity of this system, which is hardware architecture, ladder logic implementation, and system dynamics. We're relying completely on this research to guide us step by step through the logic. At its core, temperature regulation is really all about translation. We're having to translate physical, real-world heat into binary digital signals. Take a look at the flow here. Up at the top, we've got a thermocouple. That's our sensor. It's what actually detects the physical heat. That analog reality gets routed down into the PLC, the brain of the operation, right? Which processes the info. Then the PLC fires a command down to the electrical heater. That's our actuator. So it's essentially bridging that physical and digital divide to actually change the environment. Let's break down the 4 core functions of that workflow. Step 1 is the core function itself, using the PLC to automate and regulate thermodynamic output. Step 2 is continuous measurement. A standard thermocouple doesn't just check the temp once and take a break. It is actively, continuously monitoring the room. Step 3 is set point comparison. It's constantly comparing that measured temperature against a target set point we've chosen. And finally, step 4 is the binary output. If the room is hotter than our set point, the sensor spits out a logic 1. If it's cooler, it gives us a logic 0. It's just this endless loop: sense, compare, and translate into binary. Moving right along to Section 2, Hardware Architecture and Routing, Routing Sensor Data. Okay, so here we have a schematic of the actual hardware architecture. See that triangle right in the middle? That's our comparator amplifier, and it's taking in 2 inputs: the temperature it's currently sensing, represented by the Greek letter theta, and our target set point temperature, which is theta 1. The comparator basically just weighs them against each other. If theta is higher than theta 1, the output over there, V0, turns into a 1. If theta is less than theta 1, V0 becomes a 0. That V0 binary signal then drops down into the controller. Its job is to trigger that internal relay circuit, CR1, which then physically clicks the switch to turn the heater on. All right, Section 3, Ladder Logic Implementation, Software Implementation. This is where it gets really fun. Now, what's really interesting about this visual here, which is known as a ladder diagram, is this inverse Boolean relationship. Look at the input, IN1, on the left side. Notice how there's a diagonal line striking right through that IN1 contact? That basically tells us it's a normally closed contact. It's inverted. And this normally closed contact connects all the way across the rung to the CR1 coil on the far right, which is the relay for our heater. Let's actually map that visual diagram to the literal instruction table of the PLC is reading. Down at address 0, we see the instruction load not for the data IN1. That load not is absolutely crucial. It is the exact inverse relationship we were just looking at. Then at address 1, the instruction is out to our relay, CR1. Address 2 is just end. But because of that load not instruction, it guarantees the heater gets power specifically when the system receives a logic 0. Because remember, a logic 0 means the temp is below our set point. Basically, it means it's cold. So 0 comes in, and boom, the heater powers on. Which brings us to Section 4, System State Matrix, Mapping Physics to Logic. The system state matrix is a great way to organize everything we've talked about so far. Let's walk through it together. Looking at the top row, the physical state is heating required. This is what happens when our sense temperature theta is lower than our set point, theta 1. The comparator sends a logic 0 into the PLC, and because of that tricky load not obstruction we just learned about, the logic 0 actually forces the relay, CR1, and the heater status to become active, or on. Now look at the bottom row. When the target is finally reached, meaning theta is now greater than theta 1, the comparator spits out a logic 1. The inverse logic flips it, making the relay inactive, turning the heater off. So, the crucial point here is really the direct contrast between these two states. By using an inverse logic command, that load not, the system brilliantly aligns the digital binary with the actual physical goal we want to achieve. A cold physical state gives us a 0, which the PLC flips into an on command to generate heat. A hot state gives a 1, which the PLC flips into an off command so it stops heating. It's highly efficient, it generates heat only when it's strictly necessary. And finally, Section 5, Hysteresis and System Dynamics, Physical Realities. I want you to take a really close look at this timing chart. That solid, wavy line represents the actual physical temperature in the room over time. Notice how the temperature doesn't just rise up to our perfect set point and then flatline forever. That doesn't happen. Instead, it rises above the target, the controller turns off, the temperature eventually falls back below it, the controller turns on, and it rises all over again. Down below the graph, you can see the controller's output shown as these square waves, constantly cycling on and off. So in reality, the temperature is always oscillating within a specific range, which we call a deadband. And this brilliantly illustrates exactly why that oscillation has to happen. It's a concept called hysteresis. You see, that deadband isn't some flaw in the system, it's actually an intentional, highly necessary design choice. The system relies on two distinct thresholds, an upper limit and a lower limit. If the switching threshold was just a single, razor-thin line exactly at the set point, the relay would just rapidly and violently switch on and off as the temperature hovered on that exact line. Engineers call that chatter, and it will destroy a system fast. To sum up the core engineering realities here, a binary on-off actuator can literally never just rest perfectly at a single set point. It's physically impossible in the real world. So asymmetric switching is absolutely vital. The actuator only kicks on to heat things up when the temperature falls completely below that lower limit, and it only shuts off when it fully breaches the upper limit. This clever design guarantees that the system safely and continuously oscillates within a tolerance we can accept, which totally protects the mechanical hardware from burning itself out through rapid chatter. As we wrap up this explainer, I want to leave you with something to think about. We've just analyzed the really robust architecture behind PLC temperature regulation. But just look around you. How might this exact same binary on-off logic, these same load-not instructions, and the sheer engineering necessity of hysteresis deadbands be applied to other systems beyond just temperature? Think about industrial fluid levels, or massive pressure valves, or even motor control systems in huge factories. The logic we unpack today from Dr. Madian's work is literally the foundational language of automation everywhere. Keep analyzing, keep questioning how things work, and I'll catch you in the next explainer.